Hello everyone, my name is Ramya. I'm a postdoctoral student under Professor Grace Cow in Aeronautics and Astronautics at Stanford. The topic of my today's presentation is on design considerations of a lunar navigation satellite system with time transfer from Earth GPS. Now is an exciting time and the beginning of a new era for lunar exploration. Building a sustainable human presence on the moon serves as a crucial stepping stone for the success of future deep space missions. There are more than 40 lunar missions planned within the next decade by around 10 international space agencies. In particular, after more than 50 years since the Apollo program ended, NASA's Artemis mission will land humans on the moon, including the first woman and the first person of color. For the success of these scientific endeavors, position, navigation, and timing, in short known as PNT, is of utmost importance, especially for applications such as search and rescue, mission activity planning, and geotagging collected samples. Furthermore, with an increase in human and robotic activities, PNT services are needed everywhere on the moon. Given this, active efforts are being invested in exploring the feasibility of Earth-like GPS around Moon that can provide navigation and communication services. For instance, NASA has recently conceptualized the framework of LunarNet, and the European Space Agency has announced its Moonlight initiative. However, many decisions related to the lunar PNT design are not yet finalized, such as orbit, constellation, and payload. Particularly, NASA has expressed interest in utilizing a small sat platform for the future lunar PNT due to its cost effectiveness and potential for rapid deployment. As compared to our Earth GPS constellation, there are three main challenges in designing a lunar navigation satellite system, in short known as LNSS. First one is that the small sat configuration has low payload capacity. This essentially limits the size, weight, and power of the onboard clock, thereby limiting its timing stability. The choice of onboard clock is important as it determines the ranging accuracy of transmitted signals from LNSS satellite. Second is that a lower financial budget is available for developing lunar PNT. Third is that limited number of ground monitoring stations can be deployed on the moon, which implies that the LNSS satellites should require less station keeping. In recent literature, a potential orbit being investigated for lunar PNT, given its stable behavior, is the elliptical lunar frozen orbit. So the question we are interested in answering is, can we harness Earth GPS signals to alleviate these challenges in designing LNSS? The answer is yes, but utilizing Earth GPS at lunar distances pose three main challenges. First is, main lobes of Earth GPS signals are occluded by Earth. Second is, strength of Earth GPS signals is attenuated at lunar distances, which is around 385,000 kilometers from the Earth. Third is, due to Earth-Moon occultations and path loss, Earth GPS signals are not always available. Now let's look at some recent advances on overcoming these different challenges. Even though main lobes of Earth GPS signals are occluded, we can still leverage the side lobes. Recently, extensive observations of Earth GPS signals have been conducted in the NASA antenna characterization experiment to analyze the signal performance in these transmit antenna side lobes. These gain patterns, which can be seen in these images, are made publicly available for blocks 2F, 2R, and 2RM. To track the attenuated Earth GPS signals, NASA has done pioneer work in developing a high-sensitivity GNSS receiver known as the Navigator. This receiver is scheduled to be tested on the moon in 2023, and if successful, it will be the first GNSS fix on the lunar surface. Even though Earth GPS signals are not always available, based on our simulation analysis, which is shown in this figure, as well as some prior works, we can observe that for certain chunks of time, as seen here, 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 and here, the received CN0 values are greater than a pre-specified threshold. This implies that successful acquisition and tracking is possible at lunar distances in an intermittent manner. Given these exciting recent advances, the key idea of our research, as illustrated in this figure, is to design a time transfer technique wherein the LNSS satellites will listen to the signals already broadcast by the Earth GPS and process those signals to estimate timing corrections. More specifically, we design a timing filter that corrects the lower grade clock when Earth GPS signals are available, and at other times propagates these clock estimates forward in time. We also develop an Earth GPS continual outage period metric, in short known as ECOP, to analyze the visibility effects of Earth GPS on the timing stability of the onboard clock. The key contributions of this work are listed here. First, we design a small SATS-based Earth GPS to LNSS time transfer technique that updates the onboard clock estimates using a timing filter. Second, we devise Lunar User Ranging Error Metric, in short known as Lunar URE, to characterize the ranging accuracy of LNSS satellite. That is, for a given orbit and onboard clock, this metric depends on the root mean squared timing error estimated using our proposed time transfer. Third, we validate our time transfer using simulations of an LNSS satellite in elliptical lunar frozen orbit and with an onboard chip scale atomic clock. The outline of the presentation is seen in this slide. I will first explain our proposed algorithm on time transfer from Earth GPS to LNSS. Next, I will demonstrate the performance of our time transfer technique using simulated experimental data. And in the end, I will summarize my talk. First, let's start with the details of the proposed time transfer technique. The high-level architecture of the timing filter is shown here. Particularly, we design a Kalman filter framework that performs time update and measurement update to compute the clock estimates. In addition to the Earth GPS signals, we aid the timing filter using LNSS satellite ephemeris that is separately estimated using an onboard orbit determination module. Given these inputs, we first check if the Earth GPS satellites are visible. We do so by analyzing the Earth GPS continual outage period metric, in short known as ECOP. During ECOP, we only perform time update to propagate the most recent clock estimates forward in time. And when Earth GPS signals are available, we perform measurement update to correct the clock estimate. Now let's look at some more details about the signals received from Earth GPS. In this work, we utilize the Earth GPS signals received at the LNSS satellite from side lobes of the transmit antenna and a small part of the main lobe that is unaffected by the Earth occultation. This is because these transmit antennas point toward the Earth, as shown in this figure. Therefore, at lunar distances, we only receive signals transmitted from the far side of the Earth. Particularly, the CN0 values received at the LNSS satellite depend on various factors, such as the transmit power and antenna gain pattern of Earth GPS signals, occultation from Earth and Moon, as well as free space path loss. Now let's look into the details of our timing filter. We are all familiar with the general equations of a Kalman filter that has a time update as shown here and measurement update as shown here. The accuracy of clock estimate that consists of clock bias and clock drift depends on how well we can model the process noise covariance matrix, which is shown over here, and the measurement noise covariance matrix, which is shown by R over here. So let's start now with the process noise covariance matrix details, which is denoted by Q. In the time update, the clock states are propagated using a first order state transition matrix with update interval denoted by delta T. For this setup, the process noise covariance matrix is modeled as shown in this slide. While it is not important to exactly understand each term of the covariance, Note that H0, H-1 and H-2 are the power spectral coefficients obtained from the Allen deviation plot. These coefficients provide insights regarding the short-term and long-term stability of the clock. Next, we utilize the received pseudoranges, Doppler values from visible satellites, as well as ephemeris aiding from LNSS satellite to compute the measurement residuals, which are given as input to the measurement update step. The measurement noise covariance matrix is modeled as 3 components. First component deals with tracking error in pseudoranges caused by the delay lock loop, and the other is the tracking error in phase lock loop that reflects in the Doppler values. Note that both these terms depend on the received CN0. The third term models the other sources such as ephemeris error and receiver noise. Next, we devise a metric known as the Lunar URE, where URE stands for user ranging error. This metric characterizes the ranging accuracy of the transmitted navigation signals from the LNSS satellite. Unlike the Earth, Moon does not have atmosphere and surrounding buildings. So lunar URE does not require to factor ionospheric, tropospheric, and multipath effects. Having said this, the error sources to be included in lunar URE are broadcast clock, differential group delay, broadcast ephemeris of LNSS satellite, and lunar receiver noise. More specifically, the components related to broadcast clock depends on our proposed time transfer technique that in turn depends on the orbit and clock considered for LNSS satellite as well as the associated ephemeris errors. This lunar URE metric depends on the root mean square, in short known as RMS, associated with each of these error sources. Now, I will talk about our simulated experimental results that validate the performance of the proposed time transfer technique. In our simulated setup, we considered an Earth GPS constellation with 31 satellites as shown in this top figure. And at each Earth GPS satellite, which is shown in this bottom figure, we utilized the results from NASA antenna characterization experiment to model both the main lobe as well as the side lobes of the transmit antenna. We simulate the experiment for a duration of 2 months and utilize the Systems Toolkit software by AGI to model Earth GPS and LNSS satellites, as well as the attenuation of Earth GPS signals based on Earth-Moon occultations and path loss. As the next step in our simulated setup, we considered the LNSS satellite to be in an elliptical lunar frozen orbit, in short known as ELFO, and to have an onboard chip-scale atomic clock, in short known as CSAC. As mentioned earlier, we considered ELFO given its stable behavior and minimal station keeping requirements. For this analysis, we considered 3 ELFOs at altitudes of 6,500, 7,500, and 9,700 kilometers, an illustration of which can be seen in the Moon inertial frame over here. This animation on the right shows the intermittent availability of Earth GPS signals at the ELFO number 2, where the magenta lines originating from the LNSS satellite indicate the number of visible Earth GPS satellites for any given time instant. In terms of the onboard clock, we considered CSAC given its low size, weight, and power characteristics as reported in this table. And based on the datasheet specifications, a CSAC drifts for about 1 microsecond in 1 day. This table reports our simulation settings, among which the key parameters are that the CN0 threshold is 15 dBHz and the time taken to successfully track any Earth GPS satellite is 40 seconds. This figure on the right, which we have seen earlier, demonstrates the CN0 values received from PRN7 of Earth GPS, while a threshold of 15 dBHz is indicated by the black dotted line. We consider an error covariance of 3 meters for LNSS satellite position that aids our timing filter. This value is conservatively set to be around 10 times more than the position error expected in Earth GPS constellation. In the first set of experiments, we compared the three ELFO configurations for their maximum Earth GPS continual outage period, percentage of time for which the number of available Earth GPS satellites are greater than or equal to 1 and greater than or equal to 4. Intuitively, we consider the orbit with least maximum ECOP and maximum duration of satellite visibility to be the top choices of LNSS design. Based on this criteria, we observe that ELFO number 3 demonstrates the maximum duration of at least one satellite visibility, which is 99.2% of the total time. This is because it has maximum altitude of 9,700 kilometers and thereby experiences fewer occultations from Earth and Moon. An illustration of this ELFO number 3 is shown on the right, where blue indicates the number of visible satellites and the faint red vertical bars highlight the regions of ECOP. Next, the ELFO number 1 exhibits the least maximum ECOP of 3060 seconds. This is because the velocity of satellite is highest in the orbit with the lowest altitude and thereby can pass through the regions of occultation quicker than the others. In these next set of experiments, we compare the maximum timing errors across three ELFOs with the error in clock bias shown on the left and the error in clock drift shown on the right. We also include zoomed in version of error in clock bias and clock drift for a smaller section. Intuitively, maximum timing error indicates the worst case performance of our proposed time transfer. So the orbit with the least maximum timing error is more favorable for LNSS design. Based on these plots, we can demonstrate that ELFO number 2, which is at an altitude of 7,500 kilometers and is indicated by the magenta line in the plots, exhibits the least maximum timing error in clock bias of 0.26 microseconds and clock drift of 0.24 nanoseconds per second. In these last set of experiments, we determine the lunar URE metric for different ELFOs. As mentioned earlier, an important component of lunar URE is the broadcast clock component that depends on the RMS error in clock bias estimated using our proposed time transfer. In this table, we report the RMS timing errors in meter for convenience, according to which the ELFO number 3 exhibits the least clock bias error of 7.9 meters. We chose the RMS error of other sources based on Earth GPS and thereafter compute the lunar URE, which is comparable in order of magnitude to that of Earth GPS. From this, we can conclude that our time transfer can achieve low lunar URE of less than 12 meters for an LNSS satellite in ELFO, even with a lower grade clock such as the CSAC. To summarize, in this work, we proposed an LNSS design with time transfer from Earth GPS, where we developed a timing filter to update the lower grade onboard clocks using intermittently available Earth GPS signals. Through simulated experiments of LNSS satellite in elliptical lunar frozen orbit and onboard chip scale atomic clock, we validated that least maximum Earth GPS continual outage period of 3060 seconds is observed for ELFO with lowest altitude of 6,500 kilometers. Furthermore, we also demonstrated that low lunar user ranging error of less than 12 meters can be achieved even using a CSAC, which has low size, weight, and power characteristics. We want to thank AGI Educational Alliance Program for providing us with the Systems Toolkit software license. We also want to thank KDI and the members of NavLab for their insightful discussions. Thank you.